not so far.
Mm-hmm.
There are not too many similar things happening. Of course, we have a lot of conferences, we have a lot of seminars in departments, but there are not a lot of seminars which are distributed to a wide audience like this one.
Yeah,
but isn't physics review fluids trying to do something similar?
Physics fluid started, many of them asking the same question, because this is a lot of work, especially for Kelly, and I should take this opportunity to thank her for the effort she's putting in making them streamlined, announced, etc. So others have maybe slowly phasing it out. I mean, a lot of them started with great vigor, but unless there is one or two warm bodies making it happen, they're probably phasing it out. And that's the kind of question I'm asking. If it's not useful, really, I maybe. Well, the other thing that I felt was some young people, by being, since we don't have the best paper award, this is sort of a substitute for the best paper award. I mean, for whatever it's worth, we do have every semester 4 or 5 sort of young and medium mid-career people. They could say, hey, I gave the spotlight seminar kind of stuff, a small token of appreciation from the journal. Those are the two main things. But you're right, if the attendance falls down to 20s and 30s, with most of them from the organizers, then it's not serving. But today I'm very happy. Stephane, you have pretty healthy audience coming up. And I'm pretty sure we probably will reach 100. Telly, you said 180 registered, right?
189, yes.
That's Stephane because of your name and fame.
Yeah, great.
No, this is because I have a Twitter account.
Well, Stephane, then you should do us a favor in sending out the announcement for other talks.
I will do, no problem.
Thank you, thank you. And also help us in identifying good potential younger speaker from around the world.
I will.
Yeah. Greater for you also, and other Mario and other senior people who are joining us. Please help us find some good speakers who have done good work and especially published in IJMF.
Okay, sure.
Okay, Bala, I don't see Alfredo. Maybe you want to decide to go with the during the session.
Yeah, I will do the announcement.
Okay. When I admit everyone, I'm gonna unmute everyone. So if you want to speak, you have to unmute yourself, Stephane and Bala for sure.
I will do that.
Yeah, the cameras should be off, except the speaker.
I will keep my camera on till I do the announcement, and afterwards I will go into the background.
Okay, so I don't want to make experiments during a live talk, but I have this theory about Zoom, that Zoom is prioritizing audio over video, so that if the bandwidth is not sufficient, Zoom will block the video and try to allow the audio to go through. So I do not think it is gaining you a lot to turn off your videos, but I don't want to force you to verify this theory on the spot by turning on everybody's videos. Because,
the videos will be off for everyone.
You should have your video on, Stephane. So what happens is that since we are doing YouTube, whoever has this video, the YouTube will start showing. So we want everybody's video to be off and only your video to be on, so that the YouTube channel people can see you. It's a little icon on the
okay, I understand.
Yeah.
So. Okay, so maybe I will start sharing my screen so to get to the starting point.
Yeah.
Okay, Ted, you have the YouTube, right? Just if you give me a thumbs
Yes, and it's up and running. I have it all set.
up. Okay, so I'm gonna stop my video and admit people in.
Yeah, we still have 2 more minutes. Maybe we'll just.
Okay.
You want to wait still? Okay.
Yeah. I mean, because we said that 9, we should start at 9. Because people are also coming in. We are at 73 right now. I'm expecting.
Yeah, but they can join in as they come in, so there is no limit. Remove them.
Yeah. You can let them in now if you want.
They are in.
So I cannot see, is Alfredo somewhere here?
Alfredo, if you are there, please. I think he may have some conflict. So I will do the introduction. Can we get started?
I'm fine.
Yeah, okay. Good morning. I want to welcome everyone. We are about 100 participants, right now exactly 100 participants. So I want to welcome everybody to Fall 2022 IJMF Spotlight Seminar Series. This has been a great success. It's a wonderful thing to bring people of Stephane Zaleski's caliber and have them give the seminar for the entire wide world. We want to continue this activity. There are 5 seminars scheduled this semester, and I will send, sorry to flood your inbox. I plan on sending 2 emails, one a week before and one the day before. So please show your support by joining. And this is your seminar, so spread the word around. If you have students or you have fellow colleagues, please encourage them to attend and participate by asking questions and so on and so forth. This is a great opportunity to hear directly from people like Professor Zaleski. Today's talk is by Professor Zaleski. He is a professor of mechanics at Sorbonne University, one of the most prestigious universities in the world. And he is the leader of the D'Alembert's Institute at the university. His early years were in ENS Paris, where he did his PhD under sort of a world famous Yves Pommeau. So it's a very distinguished group. And then he joined applied math group at MIT and then at Paris 6. What sort of singles him out is that he is a pioneer of some really powerful multi-phaseful numerical methods that have been used for atomization, cavitation, porous media, nucleate boiling. So these are not run-of-the-mill multi-phase flow simulations. So he invented the volume of fluid method, and with people like Professor Tregwason, he has been involved in pushing the boundaries on this method. The most important thing is that his method that he develops, he makes them available to the entire world. Okay, so right now, one of the leading things is Paris Simulator, and it's available to, and it's based on Basilic's platform, and it's being used by hundreds, if not thousands of researchers, okay? He is very distinguished. He is the associate editor of Journal of Computational Physics and Computers and Fluid. He leads the ERC Advanced Project TrueFlow. He's a recipient of many awards, and I'm not going to list them. So with that introduction, I want to turn over, give all the time to Stephane. Stephane, take over. And we're
okay. Thank you, Bella, for these very kind words. I'm very happy to be here. Thank you for the invitation to this great seminar series. Of course, none of this would be possible without the help of many people. So Yash Kulkarni and Thomas Fulana are two PhD students who worked with me on the topic of this talk on the contact lines using volume of fluid methods. Sharia Afkami, Alexandre Guillon, Jacobo Bongiorno, and Youssef Sadeh worked on an earlier version of this work on withdrawing plates, microlayer, and boiling. Actually, contact lines, which I'm going to tell you about, are very useful in boiling. Hyunbin Shen, Mandeep Saini, and Daniel Fuster did further work on boiling related to this, on microlayer and cavitation. The Basilisk code is, in fact, the creation of Stephane Poppinet. It's based on the same volume of fluid ideas as Paris Simulator. Paris Simulator was also mainly written by Greta Tryggvason and Ruben Scardovelli. Alexandre Limar helped me with some of the phase field methods I will discuss. And last but not least, the Swedish group of KTH Stockholm, their name is here, Gustav Amberg in particular, helped me a lot on the contact line, and we collaborated on molecular dynamics and phase field methods, molecular dynamics done by Berg Hess, and the volume of fluid done by Shervin Bagheri and Johan Sundin based on Paris Simulator, and Peter Johansen and Berg Hess did molecular dynamics. So let's have some preliminary remarks. Okay, it's completely obvious to everyone that a dynamic contact line is a triple point between two immiscible fluids and a solid. But why this very simple prime is so difficult is that it exhibits really bothersome singularity at the triple point. The effects of this contact line and this triple point can be felt at very large distances. The effects originate at molecular scales, maybe at the scale of the nanometers, but they can be felt at the scale of 10 centimeters in some experiments. So this is really a vexing problem. And there are, in my opinion, at least in the most current codes, there is not a good solution to that problem. So I visited a great university, University of Tokyo recently, and people were asking me, is this code or that code better? And of course, I told them our code is the best, but it's really difficult to answer this question because a lot of the codes do not really deal with that properly. The main vision of the singularity is that the dissipation and the friction force diverge logarithmically. So you have a logarithmically diverging force, and to obtain it, we start from the equilibrium, which is given by this Young relation, and then we start looking at what happens out of equilibrium. So what do you observe in experiments? You observe a receding and an advancing contact angle, but in fact, this is an approximate vision of the fact. In fact, there is probably a variation of the angle in that region at small capillary numbers. And part of the problem is that the contact line is curved, so the angle measurements are ambiguous. So as a result, you define a microscopic contact angle, an equilibrium contact angle, a dynamic contact angle, and an apparent contact angle. So the apparent contact angle is whatever you decide is your main observation. So you can, for example, you can see it's easiest to observe at the scale of 20 microns. So whichever angle you observe at a scale of 20 microns is the apparent angle. The equilibrium angle, of course, is the angle that I gave before in the Young relation. It's this thermodynamic equilibrium. And the microscopic angle, that is really difficult to define, but you somehow assume that you can go to some very small scale, maybe to the boundary condition of continuum mechanics, and that's the microscopic angle. So what is the paradox? If you take this wedge shape near the equilibrium angle, and if you integrate the energy dissipation, which I've written here in the classical way for a thin film, then I suppose the thickness of the film is given by this wedge relation. Then the integral of the dissipation for a parabolic Poiseuille flow in the film grows like 1/xi squared. And so it's a logarithmic ratio. And I must say that the first time I heard this explanation, this was by my PhD advisor, Yves Pommeau, at City College in New York, and there was Benjamin Levitch in the room, and he said, you are not allowed to do that. You're not allowed to have this beta here. So here we're already in trouble, because Levitch is one of the most famous names in contact line theory. So maybe we have to do better than this singularity. Lawrence Scriven expressed things differently. He said that even Hercules could not sink a solid. A divergent force would be an infinite force in the limit of infinity small scales. So that's part of the problem, but that's not the full problem. I would like to define the contact line problem a bit more in a more clear way. And I think it's very important to define the problem clearly, because that's a little bit like the problem of turbulence. If you ask, what is the problem of turbulence? You know it is not solved, but you don't know what the problem is. So it's a little bit the same with the contact line. The first issue is, what is a good mathematical model of the moving contact line? What's a mathematical model that has good properties of convergence, being non-singular, having some smoothness? If you have a good mathematical model, how can it be computed assuming infinite computer power? And then how can you make it with the actual finite computer power that you have? So I think these are three important problems. I will try to give an answer to these three problems. For the last problem, I think we don't have the answer yet. For the first two, we are beginning to have some answers. But as I say, we are beginning, and in my opinion, it's not completely solved. So here are some subdivisions of the problem. There's the problem of equilibrium. No contact line motion seems trivial, but it's not completely solved either. There's the problem of steady motion. That is, the angle is not changing in time. The interface, the contact line may be moving, but the angle is not changing in time. And there is the problem of unsteady motion, when the angle is changing in time. And something that a lot of people worry about, which is a sub-problem of the above premise, is there a local model near the contact line? So it's very ambiguous to see what a local prime is, but a local prime would be a prime where the main parameterization of the prime are done in terms of local variables near the contact line. For example, the Navier boundary condition that I've written here is a condition that is expressed locally near the contact line. And you can also express locally the fact that the contact angle would depend on the capillary number, which we'll come back to later. So let's start with this Navier boundary condition. The slip length can be measured. This is a physical effect independent of the contact line. So you see in this table that it is sometimes as big as 10 nanometers, and sometimes it's no slip, which means that it is maybe even smaller than a few nanometers. But in general, it's on the range of nanometers, and can also be investigated by molecular dynamics. I will come back to that if I have time. And so the problem can be solved in many numerical ways, but in 2015, we started investigating it with Sharia Afkami using the volume of fluid method. So what is the volume of fluid methods? And probably many of you already know that, but it's a method where in each cell of the grid, we put the fraction of the liquid volume which is in that cell. And then we reconstruct the interface using this kind of broken lines. And this works amazingly well. I mean, even now, maybe 30 years later, I'm amazed at how well it works. I don't have the time to tell you all the virtues of the volume of fluid method, but let me show you one aspect. When you move the interface, you use these phase discretized velocities, and you move this little red interface from AB to A prime B prime. And if you place a wall here, if you have a contact line problem, you have a solid wall. And even if the wall is here, the contact line still moves, and the little interface still moves, which shows you why volume of fluid will be good for the contact line. This is what was done by Sharia Afkami. You start with some volume of fluid distribution on the grid. You use an imposed contact angle theta delta. It's called theta delta because it's the numerical contact angle on the grid to reconstruct in this last cell. Then you expand to a virtual cell inside the solid. You compute these heights, hi minus 1, hi plus 1, and the hi minus 1 height here is extrapolated. And then these heights are used to compute the curvature, and the curvature is actually the force that will make the contact line move at the desired speed. Moreover, in addition to this height extrapolation, you need to add a Navier boundary condition, which was implemented in Basilisk by Thomas Fulana. So Basilisk is an octree volume of fluid code developed by Stephane Poppinet. And so the expression for the Navier boundary condition is really elementary. But the important thing to have here is that you need the grid size to be much, much smaller than the slip length lambda to have converged simulations or smooth fields. I said the code is quad-tree, so quad-tree means that we start from this big square and then subdivide it in smaller square and smaller square and so on. Everywhere where we need details, we subdivide. So for the contact line, obviously, we are going to subdivide squares like crazy in this region. And this allows us to have orders of magnitude of range of scale. So in this case, which was done a long time ago by Thomas Fulana, we go down to 100 microns. But you will see that we have cases where we go down to hundreds of nanometers, so 3 orders of magnitude smaller. And this can be parallelized. So here the colors correspond to various processors, and we can stack on many, many processors in this small region near the contact line where, of course, everything will happen. And so this has shown you a first glimpse of the curtain coating setup. So the curtain coating setup is interesting because it corresponds to an actual application, but it's also interesting because it was the focus of a lot of debate on the local nature or non-local nature of the description of the contact line. So you have a plate that moves at velocity u, so that u is the speed of coating, and we build a capillary number based on u. And you also have a speed of falling, the velocity v, and we build a Reynolds number based on v. And you also have gravity, you have a Bond number, but the gravity doesn't play a role, at least at the small scale. And important experiments were performed by Blake, Brack, and Shikmorzaev, and what they see in the experiment is that above a certain critical velocity of the substrate of the plate, you get a sawtooth meniscus, and then you get bubbles being entrained on the plate. So you have a breakdown of the steady solution, and you have a failure of coating. What they also observed is that if you have a faster velocity of falling, then you prevent this wetting failure. So that's why it's called hydrodynamic assist. The falling curtain is assisting the coating. And Yuli Shikmurzaev was and is still a great expert on this. And he argued that there cannot be a local mobility law like the one I expressed here. You cannot reproduce this result by making the microscopic angle, the angle you solve at the small scale in your numerics, dependent on the velocity u alone. You must make it also dependent on v, which is far away from u, so which makes it non-local. There was a numerical proof of this fact by Wilson and others, and this numerical proof has was made by matching the microscopic angle at some velocity of the curtain v, and then performing simulations for various values of v. And here you have the simulations here, and you have the experiment here. So there was a total failure of matching the experiment to the simulations, which led Shikmurzaev to claim that this law does not work. But we'll return to this graph in a few slides. So here I'm just repeating what I said. The apparent length is matched in this region. If you do a close-up of the simulations by Wilson, you can see that they got to extremely small scales. So this is 10 nanometers, and so the simulation is really remarkable. And one of our objectives was try to reproduce them. Before we try to reproduce them, there were some simulation by Liu, Vandre, Carvalho, and Kumar on a reduced system. The system does not have the same dimensions as the bracket system. It is a bit smaller, which is of course nicer for simulations, and they obtained these apparent angles as a function of the capillary number. And what you have to see, these various curves here, I didn't label them, but these various curves correspond to various viscosity ratio. So this curve is obtained with a free surface, so an infinite viscosity ratio, and these are observed with more realistic viscosity ratio. You see there is an enormous influence of the viscosity ratio, and it considerably changes the critical capillary number if you have a realistic viscosity ratio. So that's the first discovery. We have further studied this reduced system. So here the reduced system has a height of 1 centimeter. And this is the result of the simulation by Thomas Fulana. So this is the whole system, again with the octree. And the color represents the horizontal velocity. You zoom on this region, we see this thin air film here, and then you see the air film is approaching the contact line. And although the microscopic angle is 90 degrees, you see there is a lot of bending, and you really have to zoom to the smallest scale to match the microscopic contact angle. But it is converging despite these difficulties. It is converging. The error in the contact line position is converging at second order. The error in the inflection point position is a bit larger, but it still is close to second order. So this is very reassuring because it seems to tell you that the Navier slip is a good numerical model. However, it's not a perfect numerical model, and I hope to be able to discuss that in a little while. There is also very good agreement with the simulations of Liu, Vandre, Carvalho, and Kumar. And so these are our simulations and their simulation, they perfectly match. And we also can get a good comparison for apparent angles. But we we see that there is something that surprised us, is that there is a lot of dependence also on the Reynolds number. The Reynolds number is based on the falling velocity, and it's absolutely not negligible. So a lot of people are aware of viscous theories of the contact line, such as the Cox theory, but viscous theories are not good enough here. The Reynolds number is not 0. Here we show 3 configurations, 3 typical configurations: the heel formation, the bead point, and the vertical configuration. Interestingly, hydrodynamic assist is strongest in the vertical configuration. And then as you increase the velocity, you move to the heel formation regime near the top of this graph. And the heel formation regime, in fact, you are losing efficiency of the assist. And in fact, you are going back to smaller critical capillary numbers. So I discussed the reduced experiment. There are other experiments, so the original Blake experiment and the Morrison experiment. I'll go relatively quickly on the Morrison experiment. It has fortunately a very large slip length, so it's easy to compare. For the Blake experiment, that's the comparison we got. We have a very much unresolved slip length here. In this case, our grid was much larger than slip length, but we'll see below that we could do better. In the Morrison experiment, because we resolved the slip lengths, things seem to be working much better. The volume of fluid seems to be matching much more closely the experiment. It's not perfect, but it's close to the experiment. And with Yash Kulkarni recently, we were able to reduce the slip length to 100 nanometers. So these are huge simulations. And also you have to take into account that we have many grid points in the slip length. So the grid size is of the order of 10 nanometers or less. And we see that as we reduce the slip length, we reduce the critical velocity or the critical capillary numbers. So you get close to the experiment. We are not quite there yet, but you can imagine that if we keep reducing this slip length to the order of nanometers, we will cover a similar range and we'll finally arrive near the slip length. But it's too expensive. We cannot reach the slip length of the order of nanometer. You see also these little graphs show you that the shape of the heel is changing as we get closer to the critical sizes. We have compared also this graph that I've shown you before, showing the apparent contact angle as a function of the flow rate. And as I told you before, this was a note not for you, but for my group. There's a huge range of uncertainty in the BRCA experiment, and we match actually not here, but we match somewhere here, and so we get a completely different result, also because of the different type of matching. So the jury is still out because we do not fully reproduce the experiment in the range, but we're getting closer. Another interesting result of the volume of fluid method is the confirmation that the curvature has a singularity. So this is something that was known before, but if you use a slip length, you remove the original singularity of the dissipation. You replace the logarithmic singularity of the angle of the derivative with logarithmic singularity of the curvature that is shown nicely here. We have found ways, better model than a slip length in the sense that remove this singularity, but I will not have the time to discuss them today. Let's move on to the plunging plate experiment. So this is similar to to the curtain coating in the sense that it is also an advancing contact line. And you also have this thin earth film with this solution by Benny and Timpson, which was considerably worked on by Jens Eggers. And we tried to reproduce that. Well, still in the curtain coating, but we try in a small region to match the plunging plate theory. And as the capillary number is increased here, we get close to the 1/2 slope as we approach the critical number. So there is a small range where it works, but we don't have a full reproduction of the Benny theory. We can change the direction of the plate, and now we are leaving the curtain coating realm, and we can look at the withdrawing plate. The withdrawing plate is a very different problem from the curtain coating and the plunging plate, because in the withdrawing plate, the critical capillary number is much smaller. You have capillary numbers which are much smaller than 1. And for this small capillary number, the Cox-Voinov theory applies. So I'm going to explain what this theory is in a moment. And you say that the contact line is receding in that case. So these are results obtained a while ago using an older code called Jerris, which is essentially the same as Basilisk, but with less parallelization capabilities. And in that case, here I give an example at moderate Reynolds number and unit viscosity ratio. They said the capillary number is small. And this flow exhibits the so-called Landau-Levitch-Deragin transition, where at large capillary number, you get a film forming here, and at small capillary number, you have the contact line stays at a constant height. So this is a very interesting configuration, at least from the theoretical or mathematical point of view, because this transition will be very sensitive to tiny details at the contact line level. So in this case, it's not enough to be able to simulate any contact line by your code. You really have to get the small scale right. So when we perform these simulations for each angle and size, we determine a critical capillary number. So how do we determine this number? We increase the capillary number here from 0041 to 0049, and we see a transition number where it seems that you will not reach anymore an asymptotic value of the height. So remember, the height is this height here, and we define this as the capillary number. If we plot the capillary number as a function of the grid size, we get a rather disappointing result, which is that the capillary number depends on the grid size. The critical capillary number depends on the grid size. So this is, of course, a bit disappointing. But it turns out that this dependence is very simple. It seems looks here like a parallel. And we can explain this dependence. Of course, this is not a cure to this problem. The cure is in what I've shown before. The cure would be to have a slip length model and a grid size much smaller than the slip length. But these small grid sizes of 10 nanometers are not always available. So we have to do something else. And we can use lubrication theory to predict how the critical capillary number depends on the angle and also on the grid size. So this expression implicitly gives you the critical capillary number for a given grid size and a given angle. And it is there are several versions of this theory, and it matches a prediction made by Eggers. It is based on Cox theory, where Cox theory predicts the variation of the angle with the capillary number. So this theory tells you that the angle at distance r depends on the capillary number and the equilibrium angle through this function g, where the function g for a free surface has this relatively simple form. And we can, in fact, extend this theory. This theory does not necessarily use the equilibrium angle. It can also use a dynamic angle, that is a microscopic angle that depends on the capillary number. And some nice thing we can do in this simulation is try to verify Cox theory. And well, it works, but to a certain approximation. That's why I put verification quotation mark. We have a log dependence, but not quite with the right slope. So much more powerful simulations would probably be required here, but since it's an asymptotic theory for small capillary number, you can have, you don't expect any big surprises here. What is maybe not a surprise, but an interesting thing is that with the withdrawing plate, we get this relatively clear theoretical description at a small scale, while with the plunging plate or curtain coating, such a simple theory is not available. Now I leave the issue of the withdrawing plate to go back to another configuration, which is the shear droplet experiment or simulation. So you have two plates and this rectangular droplet of water between the two plates. Outside the water, you have water vapor. So you have this very precise description of the parameters here. And these precise parameters are going to be simulated using molecular dynamics. And then molecular dynamics is going to be compared to two continuum methods, the phase field of Amberg type and the volume of fluid. The system now has 4 contact lines, 2 advancing and 2 receding. And in volume of fluid, we will use a localized Navier boundary condition with a constant contact angle. The contact angle will be matching the molecular dynamic simulations. So this was published in this paper and also in a recent JFM paper. And so you can look at the streamlines. For example, you have this characteristic double folding streamlines in the air and these simple streamlines in the liquid. And you can do molecular dynamics on that. So the original aspect of these molecular dynamics is that they are performed with a realistic model of the silica and water atoms. And as a result, you have hydrogen bonding between the silica atoms and the water molecules. And then the hydrogen bonding is a strong bond that in fact prevents slip. So there's extremely small slip in this model. We're not able to really measure the slip of the molecular dynamics. So it is close to 0. And we compare this with the phase field or diffuse interface method of Amberg. And one of the nice things about the Amberg model is that it works also with no slip. I will explain that later. But this model also enters in the general area of diffuse interface methods. And so these diffuse interfaces were promoted by Yves Pommeau and others. And in particular, Yves Pommeau has encouraged people to reproduce the simulations of Pierre Sepercher, who obtained a contact line in a water vapor system described by the phase field. I will say what the phase field is in a moment. So you have the contact line here. It seems to arrive at an angle on the interface, and then here the lines are vertical. And if if you think about it, you can find a mathematical proof that the isolines of the phase field must be vertical. The proof was communicated to me by Matthijs Fricke. So what is the diffuse interface method? In continuum mechanics, we often work with sharp interfaces. That's the basis of the volume of fluid method, the front tracking methods, and many others. But you can also decide to work with a diffuse interface where, for example, the density varies over some characteristic distance. This is usually coupled with a free energy, which has two minima, one for the liquid, one for the vapor. And van der Waals has shown that you can obtain this by adding to the bulk free energy, this interfacial free energy proportional to the gradient squared. And Kahn and Hilliard expanded this to involve write the gradient instead of the derivative as van der Waals did. It's often called the Kahn-Hilliard model, but it's really van der Waals model. You can describe arbitrary two-phase flow by making the density and viscosity dependent on the order parameter C. But what is really described by the model I'm going to give is a model with basically two species of molecules. So the Gustav Amberg's model is incompressible. From here, the Navier-Stokes equation is supplemented by this phi grad C term, which was also brilliantly used by Alfredo Sondati for his simulations. This term is a surface tension term, but here phi, instead of being the surface tension times the curvature, phi is chemical potential. And this chemical potential is a function of the concentration or the order parameter. So you have a double Laplacian here, so it's a fourth order model in C. This fourth order equation is central because this is the equation that creates this thick interface. As I already said what the bulk energy was. The boundary condition that's especially interesting, as I said, you have no slip on the solid. This is allows you to model no slip systems. And the motion of the contact line is made possible despite the no slip by evaporation or diffusion. And the evaporation diffusion is described in this relaxation condition. This is a condition on the surface, solid wall that basically drives the system to relax the surface energy given by G to its equilibrium values. And the equilibrium values of the surface energy are parameterized by these gamma 1, gamma 0, and gamma parameters, which are the surface tensions. And it's designed to have an exact solution corresponding to have the Young-Laplace relation. There is a parameter here, mu f, which is dissipation parameter, which is called the contact line friction. Has the same dimensions as viscosity. As I said, the equation for the chemical potential is fourth order and it's a bit awkward. But if you expand around the equilibrium state, which is C equal 1, then you get an ordinary peak and diffusion equation. So the system has ordinary diffusion except on the interface. So the solutions look like this. And you can see if you zoom here, this very thin green line that maybe you don't see, but when I follow them with my pointer are the isolines of the order parameters. And you see this flux through the isolines, which is the evaporative flux. So that's not the velocity, but the diffusive flux. After we have set up all this machinery, we can compare the three methods. The molecular dynamics will give you these jagged lines here with the phase field, which gives you this red curve, and the volume of fluid with local slip. It works very well in the bulk, but it's not perfect near the boundary condition, but it gives you an idea of what can be achieved up to now. The models have many parameters. and investigations are still in progress to try to improve the connection between these various methods. And so, in particular, if you have a Cox solution, it would be valid somewhere here. So at much smaller scales than the size of the channel, but also at larger scales than the small molecular scales. So it's not easy to see a Cox solution here. It's also a problem because the molecular dynamic system has a gas, a compressible gas, so even a very small density gas, while the phase field is incompressible. So it would be more realistic to use the Seppershare model, which was a true van der Waals model, in which instead of using the other parameter to get the surface tension force, you actually use the gradients of the density with this stress tensor here, which is called the Korteweg stress tensor. And so we have simulated that with Basilisk, and you can get this contact line motion on a small droplet with Basilisk. This is still under investigation. Another potential improvement to the contact line studies that was made possible by the study of the phase field is the use of TZ-Kian's generalized Navier boundary condition, or GNBC. So if I consider the pair of boundary condition of Amberg for the phase field, so you have, as I said, no slip for the velocity, and for the other parameter, you have a relaxation condition. You can combine the two, which I think is a very clever use of the Onsager method for deriving dissipative motion. Now you have here a Navier boundary condition. If this is equal to 0, this is a Navier boundary condition, but with some additional force on the wall coming from a dissipation coefficient L of C times the gradient of C. And L of C is exactly the same that the one that appears here on the right-hand side of the Amberg condition. So an L of C is sometimes called the uncompensated Young stress. That's the energy that arises because the contact angle is not the equilibrium contact angle. So as you move the contact line, you are going to gain some energy, and that's called the uncompensated Young stress. If you use a Tench solution, which is an exact solution in the bulk, you can understand the uncompensated Young stress here, and you can see that the exact tension solution gives you a 0 uncompensated Young stress. So this GNBC condition can be seen here as an improvement to the original Navier slip, and I will explain why on the next slide. If you expand the GNBC near the tension solution in close to the sharp interface limit, you can replace the dependence on the other parameter by this F epsilon function, which was already suggested by TZ-Kian. For the tension solution, you get this shape, and now you have a steady state contact line motion that is possible. But you can also show that this term here, and that was shown in great detail by Yash Kulkarni, this term here with the thickness of the interface in this F epsilon function also kills the remaining singularity of the contact line, that is the logarithmic divergence of curvature, is also killed by F epsilon. So you can also find the speed of motion of the contact line, like here, where epsilon is the thickness of the interface. I must say that the GNBC is frequently used nowadays in simulation of the contact line, but with the F epsilon function, the smooth delta function replaced by a real delta function. So this was in fact used by Greater, Tryggvason, and Tom Chen. The difficulty of having a delta function is that then the angle difference theta minus theta x here depends on grid resolution. So there is a fake convergence of delta function GNBC. So which basically the delta function GNBC is just a device for forcing the contact angle to be equal to theta x. But if you want a more realistic dynamic angle, then you have to keep a thick interface. So could we use the GNBC with a smooth F epsilon? Well, it removes the logarithmic singularity, but there are still some difficulties. The grid size must be much smaller than epsilon, which is the order of nanometers. So we will reach the same problems we had before with the ordinary slip. That is, we need very small grid sizes. So I will want to finish with reminding you the three original problems. Maybe a good mathematical model is the GNBC. Maybe we can compute it on arbitrary grids with infinite computer power. But how can we manage finite computer power? Well, one way would be to use subgrid modeling using the Cox solution. The Jean and Malio and others have shown that you can work at a grid size delta and still get the small scale angle theta. But the difficulty is that for this to be valid, you need to have a range of validity of Cox theory between the microscale and the outer scale. And having this finite range of validity with the grid size in the middle requires very, very small capillary numbers. So this is not always possible. And you have to, I will conclude on this. If you really want to make simulations which are correct with finite computer power, we have to find other asymptotic theory. We have seen the Benny solution for the coroutine coating. We need other types of asymptotic matching, perhaps matching with numerically developed solution in the contact line regions at small scales and larger scale solutions at the larger scale. So I will conclude with that, and we're happy to take any questions.
Many thanks, Stephane. So, Stephane, thanks a lot for your very nice presentation. I think that we now, we switch roles with Bala. And can you hear me, yes?
Yes.
Yes, okay, perfect. I saw no reaction. So now the paper, Stephane can answer questions. Are there questions? You just raise your hand, unmute yourself. Send something in the chat. But in the meantime...
Okay. If you want, I can start, Alfredo.
Please, Marco.
Hello, Marco.
Stephane, how are you? Fine. Thank you for this excellent presentation. That was really exciting. Many results, really. So, 2 points. One point is that I'm working a little bit with stochastic hydrodynamics. So, in fact, introducing fluctuations, which is resembling a little bit the molecular dynamics, but with a higher, let's say, larger scale. So one solution could be really to think about the fluctuations of what is happening at the surface. Since this is introducing, let's say, a kind of a fake force due to the fluctuations. So this could be, I think, a possible direction, a very interesting direction, I think. The second point, in a paper, let's say some years ago, I introduced with our collaborators the idea that instead of prescribing the contact angle, one should prescribe the force, because the contact angle is the result of the force. So this is reminding me a lot of the GNBC, the one of the last slides, where you put the sigma multiplied by cosinus theta minus cosinus theta equilibrium, because in fact this is, except for a radius, is a force. So, and so in fact, you're introducing the force considering the contact angle, or the equilibrium contact angle. So the theta at the end is an outcome, it's not an input anymore. You know? So this can be another way to see. So there are, let's say, these are the two alternatives I see with respect to your, let's say, to your presentation today.
Yes, thank you. Thank you very much, Marco. Both suggestions are very interesting. Rough contact line and rough surfaces are obviously extremely interesting, and we're very keen to start working on them. On the GNBC, I fully agree with you, and I want to mention that actually we're working hard on GNBC, especially Mattis Fricke, Thomas Fulana, and Yash Kulkarni. I see that Mattis is here. Have made a lot of progress on the use of the GNBC, and they don't have time to show it in my talk, but they managed to obtain very nice results along the lines I've presented here.
Yeah.
Okay, thanks. And I think there is a question of Bala first, and then a couple of questions then by Nicholas, and then a question on the chat. Bala first.
I had the same question as Marco. When you are going to nanometer scale, surface roughness will become unavoidable. What I wanted to ask was, when you introduce roughness, that will change the modeling from a deterministic approach to a stochastic approach. Sometimes that may offer avenues for you to attack the problem more easily than a very deterministic approach, especially when there are singularities and so on. So I'm not really adding anything. I'm just sort of reiterating that maybe a stochastic approach may be a viable one.
Yes, in fact, you have a kind of game you can play. You have a deck of cards, and you can interchange the cards. One of the cards is the slip, the other one is the roughness, and using the phase field or the GNBC. And for example, you may want to ask what would be a better effective model with roughness. For example, is this going to increase the slip? Is it going to increase the dependency of some intermediate angle on the velocity? So these are very much areas under investigation now. We hope to be able to use very accurate DNS codes, that is codes that really resolve the very small scales with roughness to see what happens at the very small scales. There was already some work by Amberg, Bagheri, and on this topic of rough surfaces.
Thanks. Now there is a Nicolas Valle.
Hi.
Hi.
Hello, everyone. Thank you, Professor, for this very interesting talk. My question was about the numerical methods itself that you've been using and have presented in this talk. Where does all this leave us in terms of conservation of these global properties? I'm thinking about conserving momentum for the over the interface for surface tension, and also energy. I understand that most of the methods are developed from an energy perspective, but I don't know how relevant is it from your perspective conserving linear momentum, considering the bigger scale.
Okay, so mass conservation is relatively easy. We have a few debris, for example, when we are on the, I have not really given details of what happens with the near the contact line near the critical capillary number, but the interface fluctuates, and you're on the verge of creating these small bubbles that will be entrained on the plate. And here you may be losing some fragments of mass. So that would be a source of concern. And for energy conservation, we have unfortunately still a defect of many DNS of interfaces, the so-called spurious currents. And although spurious currents are reputed to have been cured, they have not been completely cured, and they are more important spurious currents usually near a contact line and elsewhere. So the spurious currents are kind of energy non-conservation, because you are basically constantly dissipating energy in the spurious currents coming from the numerical surface tension. So yes, there are some issues still with basic issues such as not dissipating energy. Some people want to do a surface tension modeling in numerical methods that would be strictly energy conservative. Actually, that was an idea of Jacquemin, who was one of the inventors of the phase field. So if you do that, you will kill the spurious currents, but it is tricky. No one has really developed to a large extent an energy conserving DNS method for interfaces.
Thanks, Stephane. I will read one question from Quan Huang, and then there are two other questions live. So Quan Huang asks, thank you very much for your presentation. Is it possible to use the Cox model with no slip boundary condition for a very small CAN number?
Capillary number.
Yeah,
capillary number. Yes. Basically, if you have a no slip boundary condition, you have to rely on numerical effects to make the contact line move. So if you have grid size or grid scale defect to your no slip condition, yes, the answer is yes. But if you have a perfect model which perfectly implements the no slip boundary condition, then you cannot make the contact line move. So even if the capillary number is very small, it will not work. So my answer is it depends. It depends on how accurately you are imposing no slip.
Thanks, Stephane. Then there is a question by Ali Rabeh and then by Mathis Fricke. First, Ali.
Yeah, I just wanted to ask you, what's the role of mobility between the two immiscible fluids at the substrate, at the solid substrate? Do you assume it to be one, saying that the two fluids cannot mix together?
No, mobility. No, there is mobility is not related to mixing. It is the interface thickness which creates some of the mixing. You have also a mobility coefficient for the chemical potential, which is related to the diffusivity of one phase into the other. So that's not related to contact line. And you have a relaxation parameter, a kind of mobility on the surface, which is Amberg's contact line friction. So I think these are the three mobility coefficients you can find, and they are related to different physical effects: diffusion, contact line viscosity, and interface thickness.
Perfect. Thank you.
Thank you. And Mathis Fricke.
Yes, Stephane, thank you very much for this very nice overview. Hi. So I liked very much that recent result in the curtain coating where Yash and you and others showed that essentially the simple Navier slip seems to be able to reproduce the hydrodynamic assist effect despite earlier conclusions. But I would like to come a bit back to this finite computations power problem.
Mm-hmm.
Yeah, so I think these simulations, they require huge computers and long simulation times, even in 2D. So I think that's why the subgrid modeling approaches are quite important when it comes to, say, apply it to some engineering problems.
Mm-hmm.
So at some slide, you had this subgrid evaporation as a keyword. Can you maybe say a few words more about that?
Okay. And so, you know, in a phase field, we are convinced that what makes the contact line move is evaporation. And so you could imagine that you could add evaporation to volume of fluid, that this would work, but it is not so easy because you would have to define precisely the rate of evaporation as a function of the parameters near the contact line. So there is some work currently being done by Gustav Emberg and Thomas Fulana to try to, based on the earlier work by Feng and co-workers. And yes, there could be some aspects like that, but it is tricky. In my opinion, it is quite tricky because evaporation cannot really be subgrid. You have to evaporate at least the interface in one cell of the volume of fluid, right? So, but why not? I mean, you may. It all depends on the length that will occur. You could define an evaporation length, which would be the analog of the slip length. If this length is 100 microns, you have no problem. If this length is still 10 nanometers, you still have a problem. And so you still need a kind of asymptotic matching to match this very small scale to your grid scale.
I see. Thank you.
Thank you very much, Stephane. I think I don't see any other questions. I think several have been asked and the subject was covered very well. Thanks a lot for your inspiring ideas. And if there is no other question, I would like to thank you. Thank you very much, Stephane, again. Thanks a lot.